Okay, so now we've gone over complex and real valued eigenvalues. So what if we have real valued eigenvalues that repeat? So this is an example of when that is going to happen, and we'll go over it. I'm pulling it directly from the written description that I've included of how to do this. The other thing I want to say that's going to be a little different about this video is that the written description does a great job of explaining what I've written here and why it is what it is. So I'm going to direct you there just for the first part. It's like literally, I think it's like the first paragraph or 3 paragraphs or something like that. It's just basically down until the first example. So if you look over that, it does a great job of explaining kind of why we use this as our, well, I'll get into what this is as well, but when I get here, I'll point it out. So I think you will do best to look over that briefly, and then what I'm going to do is I'm going to work out the first example. I'm not going to do it as an initial value problem, but functionally the difficult part of the process is kind of I will work through that, and we'll talk about kind of what's going on here. So let's just jump right into it. So let's find our eigenvalues. You know, by this point, you're probably pretty confident that that is like always going to be step 1. In fact, I'll just jump right to the determinant. So sometimes this is called the characteristic polynomial because it kind of characterizes the matrix. So if you hear that, that just means this thing, the determinant, the determinant of A minus lambda I. So if we do this multiplication, I think we end up getting, we get this. Which means we get lambda minus 5 squared equals 0, which means the only eigenvalue we have is 5. Okay. Now the idea here is that, okay, cool. So one of our solutions, we've done it a couple times now. We know it's just going to be, oh, actually, I guess we need the eigenvector really quick. So if we plug that in, we subtract it off. I think we get 2, -4, 1, -2. This makes sense because look, we've got a nice scalar multiplication going on there. So if we pick, for example, it looks like if we do maybe 1, -2, this is a perfectly good eigenvector. So this could be our Z. Okay. So what does that mean? Well, that means one of our solutions is kind of breezing over this because we went over this in another video. One of our solutions will look like this, right? This should look kind of familiar. But again, now we're sort of stuck, right? Because we only had the one eigenvalue, which means we can only get the one eigenvector. And so we're not really sure what to do. So that's where this piece comes in. So if you think back, you really rack your brain for differential equations. I think you'll remember when we had repeated roots of our characteristic polynomial there, when we were doing second order differential equations. We ended up using, I think it was t e to the t. This was our guess or something of that form. So again, the written description goes through why t e to the t doesn't work. Basically, the long and the short of it is you guess something of that sort. You guess like whatever it is, like zt, maybe z2 t e to the lambda t. But if you run through the operations with this, you take the derivative, you plug it in like we did in the first video, this won't work. So what ends up happening is you get, we use this as our guess instead. So we guess that our x2, I guess, of t is going to be, it's going to be z1. So this, remember, z1 is this, right? This is our first eigenvector. So z1 times e to the lambda t, or I'm sorry, I'm missing a t here. z1t e to the lambda t plus z2 e to the lambda t. Now I believe in the notes over there it calls z1, it calls it like this n with a hook on it, and then z2 it calls rho, which looks like a p when I write it. That's rho. But really it's just the same thing. And then so the tricky part here is, okay, cool. So we've got our other solution. We know lambda, obviously, because we only have one lambda. We know z already. The only thing is, what is this z2? I looked a couple places to try and get a geometric intuition for why this is the case. But I think that honestly, the reason this works in this situation is simply because if you run through the operations using this setup with the definition that I'm about to give you for z sub 2, it works, like it solves the differential equation, and that's really all we need, or rather the system of differential equations. So basically, so what's z2? I've been holding it back from you. So we take our, so normally we would do a minus lambda I times z equals 0. So z2, what we do a very similar thing instead. So this was for z1, right? So now we want to know z2. If we just set it equal to 0, we'll get the same number. So what we do instead is we set it equal to z1. Now again, this feels a little weird. We'll walk through the problem. I guess we've already started, because this part, like this is kind of what I was talking about. Once you kind of get used to doing this, it's real quick, because you're just finding eigenvalues, eigenvectors, plug and play. So great. So let's go ahead and do this. So in our case, we want to know when a minus lambda I, which was, I believe that was this matrix, right? We want to know when, instead of equaling 0, when we multiply this times some vector, when is it going to equal 1, negative 2? Right? This is just the specific example of this applied to the problem. Okay. So if we perform this operation, I think you'll see pretty quickly that what we get is, if we get a kind of a similar system, we get two. I'm going to use the z1, z2 notation for the components of this vector. I hope that's okay. So 2z1 plus z2 equals 1, not 0. And we need to know when, well, okay, so you can probably see what's going to happen here, but 4z1 plus, or I'm sorry, minus 2z2 equals negative 2. Do you see that these equations are the same equation? If you divide this one by negative 2, you get this one. So remember, that's what we're expecting. That's kind of why one of the byproducts of doing this eigenvalue calculation, it's related to the definition. So we can just focus on this guy. So help me find a z1, z2 that works here. Let's think. So we want, what if we just did z2 is negative 1 and z1 is 1? Would that work? We get 2 minus 1 is 1. I think that works. So then so if we do, remember, these are the components of our vector this vector. So I really hope the subscripts are not confusing. I'm really trying to put the little hat on it when it's a vector and not when they're components. But if it is, well, I guess I can't fix it because this is pre-recorded. But hopefully that makes sense. So we get the vector z2 is going. We're saying it's 1, negative 1. And if you check, this is a good sanity check. Is this vector, or rather, are these two vectors linearly independent? And I think they are. Right? There's no scalar we could multiply one by to get the other one. We just do this very different. Which is exactly what we want. We want two linearly independent eigenvectors that solve this equation. So cool. So what does that mean for our x2? Well, let's plug everything in. Remember, this was our x1. So now we're doing x2. I wrote 1 again. Brain's a little fried right now, I suppose. So we're going to get our z1, I believe, was this guy. So 1, negative 2, sorry. And then t, e to the 5. That was our eigenvalue, right? I'm not going crazy. Yeah. E to the 5t plus, now we've got our new vector in place, so we've got 1, negative 1, e to the 5t again. So remember, now we've got an x1 and an x2 to contend with. Both of these solve the system. And again, this is something you can check. You can always plug in both of these for, actually, maybe I should quickly go over that. So when I say you can plug it in and check, what I mean is, if you go back to the original problem setup where we have, where is it? Did I not write it down? Oh, it's over here. Oh, classic. So if we go back to the original problem setup, if you plug in x1 and x2 for x, and you plug in their derivatives here, and you perform the matrix multiplication, you'll get something that works. You'll get something that's kind of I would say clearly equivalent. Like things will cancel nicely, and you'll get something that's like 5 equals 5 or 0 equals 0, or maybe like 2e to the 5th equals 2e to the 5th, right? So something that's obviously equivalent. And that's a good sanity check if you're curious. And again, that works with a general solution as well. But again, so we've got two kind of specific solutions here. So we're going to take their linear combination, and we're going to claim that x of t, the general solution, is c1. So c1 times x1. So this is going to be a little bit weird format compared to what we've done before. So this is the same, but then remember, we're going to do c1 times all of x2. So you got to remember that it's c1 times x2. So now we can write it in. I gotta say, one of the biggest errors I see when I'm helping people with this kind of thing is they just multiply the c2 times the first term and they don't distribute it. That is not ideal. We want to make sure we're distributing it, or else the properties won't hold. I will say, if it makes it easier for you to wrap your head around, feel free to distribute. Once it's written out like this, feel free to distribute this C2 kind of into these terms, like sit them out in front. But it's not necessary. I think this is a fine response on an exam. And look at that. In very little work, realistically, we've gotten to a general solution for our differential equation. And I believe this is what they got. If it's not, it's probably close. Yeah. Oh yeah, so they apply, this is what they got, but they apply an initial condition. And yeah, so that initial condition changes some things. But yeah, so great. So if this is good, then thanks for watching, and hope it made sense. Hey, so quick side note, I'm back. I just checked the written description. It looks like they got a different eigenvector here. And what I just wanted to point out is that theirs is correct, and I believe mine works as well, because the only necessary thing is that it solves this equation, right? So the one that they used was 0, 1, which you can see also solves this equation, but 0 and 1 have the same relationship as 1 and -1 in that 0 is, I mean, arguably it's simpler, but basically the relationship that they develop is something like this. But I hope you can see if you pick P1 equals 1, you get mine, and if you pick it equals 0, you get theirs. But I just wanted to point out, like, there's nothing weird going on there, and anything that solves this equation, any vector that solves this equation, is perfectly valid. So don't super worry about that if you like get a different vector. Like I said, the main thing is that this relationship between the Z1 and the Z2 is maintained, or in their case, it's like a row 1 and a row 2. Yeah, so don't stress about that if you get something slightly different, because it's still likely accurate. So,